Hi, everyone. My name is Rimple Sandhu. Yeah, as Eric mentioned, I'm a researcher in the Computational Science Center at NREL. And I've been at NREL for about 4 years now. Joined NREL right after I finished my PhD up north in Ottawa, Canada. And I joined NREL in the Wind Energy Science Group as a postdoc, and then I moved to the Comp Sci Center. So today I'll basically talk about the work I did during my PhD, and after I came to NREL, I still maintained contact with my old research group. So I meet with grad students monthly, bi-monthly, and they're still continuing the work in Inverse UQ. So I'm still trying to make myself acquainted with the recent advances in Inverse UQ, even though I'm not exactly working in this field at NREL. So I'll just basically talk about three things today. Introduction to Inverse UQ, what it is, why we need to do it. Then I'll talk about the case study, the actual system that we tried to do Inverse UQ on, and the proposed solution that we had. And in the end, I'll talk about a little bit about how this could be extended to wake modeling. Feel free to interrupt me if you have any questions. Just want to make sure this is, not a very formal talk. If you have any questions, just feel free to interrupt. So let's start with Inverse UQ. So what is Inverse UQ? It's basically you're trying to calibrate the parameters of a model that has some tuning knobs using some observational data. And you want to do that while including data and modeling uncertainties. We'll talk about what those are. But in the end, you end up with a probabilistic predictive model that you can use to predict your quantity of interest and do outer loop applications like forward UQ or design optimization or sensitivity studies. Inverse UQ.
Sorry, Sandhu. Sorry, did you want to change your slide? We're still seeing the first slide. At least I am.
Yeah. I'm still in the first slide.
Okay. Apologies.
Yeah. So Inverse UQ is also called system identification in structural engineering. Sometimes it's also parameter estimation, model fitting, parameter calibration. There's a bunch of names of it, but it's basically you're trying to calibrate the parameters of a model. And it's a combination of two things. You're trying to solve an inverse problem, right? Where you have data. So your data could be, field data collection. It could be coming from high fidelity simulations. For example, in wind energy, it could be coming from high fidelity CFD runs. And you have a model that has some tuning knobs. So it could be purely data driven, like neural networks, deep learning. It could be empirical heuristics, like we see in wake modeling. And it could be some low fidelity representation of physics the model has some tuning knobs that needs to be tuned. So inverse problem is all about marrying these two components, observational data and your model that has some tuning knobs. And you want to do that while quantifying uncertainties. So there's data uncertainties. So when you collect data, you usually have uncertainties in it, and you're not capturing the entire state of the system. So there's uncertainties in that. There's model uncertainties. So model by definition is an approximation of the physics that you're trying to represent. So there's always going to be a mismatch between the data and the model. It's also called modeling error or model discrepancy error, but it's basically the stuff that's not captured by the model that you proposed, but is present in the data. And then there's model selection errors. So you could have a bunch of models that fit the data nicely, but there is some uncertainty on which model is the best to go. So I'll talk about that aspect. So basically, to summarize, you're trying to solve an inverse problem while trying to make sure that the uncertainties are captured in your calibrated model. Let's see if I can go to the next slide. Okay. Oh, yes, you were right. I was looking at a different screen. Okay, my bad. Okay, can you see the slides moving forward now?
Yes.
It's in slide 3 now.
Yep. Yes.
Okay, my bad. Yeah, sorry about that. I was looking at a different screen. I had another presentation open. Okay, so hopefully you guys, I talked over this, but this is basically what it was. Yeah, so inverse problem plus UQ. So why there is a need to do inverse UQ? So when we're trying to model a system, there's laws of physics, right? That has very good extrapolation capabilities because they have less tuning knobs and you don't require much of training data. On the other hand, you have purely data-driven component. So deep learning, neural networks, they have a lot of tunable parameters and they require a lot of training data. But the good thing is their computational cost, the forward run, is very low. So you can use it for your outer loop applications, design optimization, forward UQ, and stuff like that. And so the goal is to find a compromise between the two ends of this modeling spectrum. So you want a low to mid fidelity engineering model that's somehow captures the physics, that has some physical components, has some data-driven components, some empirical components, could be heuristics. So in the end, you end up with a model that has a manageable number of tunable parameters, requires manageable amount of training data, has reasonable computational cost, and has some extrapolation capability. So extrapolation means you're trying to predict outside the regime of your training data. So this is what you're trying to do. Now, to do this right, you need to capture uncertainties because uncertainties are there in the data and the model that you proposed. Maybe your empirical equations are not capturing the entire thing. There's some heuristics that you're not sure about. So there's a lot of uncertainties to go. So if we want to do this right, we have to capture the uncertainties, and that's why we need to do inverse UQ. So I'll talk now about the system that I was dealing with. As Eric alluded to, it's not exactly wind energy, but let's see if I can play this video. So I want you guys to see this video and I'll explain things over it. So it's basically a rigid wing with a uniform cross-section undergoing self-sustained oscillations. So it is an aeroelastic system, but it's a single degree of freedom system since this is a rigid wing. So there's only pitch degree of freedom. There's no external forcing. It's a self-sustained oscillation. So I guess you could relate it to wind energy, but it's not exactly wind energy. Now, why do we need to understand this system and why is it important? Well, self-sustained oscillations. So whenever you hear self-sustained oscillations, you quickly jump to, oh my God, you can extract energy from it. You can generate power from it. So we need to understand what kind of aerodynamics we're dealing with, right? It could be nonlinear aerodynamics, unsteady aerodynamics, what kind of aerodynamics there are. So by capturing the pitch displacement, can we then figure out what kind of aerodynamics we're dealing with in terms of parametric representation? And this is also important because this type of phenomena could be observed in low-flying aircrafts like unmanned aerial vehicles. So it could be, it's important in that respect as well, because you don't want these aircrafts to have suddenly these self-sustained oscillations, because it could be detrimental to the aircraft and the aircraft wing. So both positives and negatives, but the key point is we need to understand the aerodynamics, right? And all we have is the pitch displacement measured from the wind tunnel. So this is a wind tunnel, low-speed wind tunnel in Royal Military College of Canada in Kingston, Ontario. So we did testing there. So there was some prior understanding about the physics of this self-sustained oscillation. So this is on the bottom here, you'll see the captured displacement from the wind tunnel. And so we need to understand this complex aerodynamics. This only happens for transitional Reynolds numbers. There is some dynamic instability leading to exponential growth in amplitude, as you see in this time history. And then there is a stabilization to a constant amplitude around 5 degrees. So there is some flow separation phenomena going on on the airfoil surface. So what is the challenge in trying to, understand this aerodynamics using this captured time series pitch displacement response? Well, the thin airfoil uncertainty theory cannot be used because it cannot capture the nonlinearity that we have. So we can't rely on that. We can do viscous CFD with it, but it may be an overkill because this is a single degree of freedom system, and you may want to use this calibrated model for some purpose, which requires, thousands of runs of this model. So we can't do that with CFD. So we want to have a model that's somewhere in between. Obviously, we can't do deep learning because I just have one response, one realization of the pitch displacement. So I can't train a deep learning model with hundreds of thousands of parameters. So that's not going to be possible. So we need a physics-based low fidelity solution. And we need to capture this aerodynamics in a parametric form. And then once we have that, we can use it for different purposes. So let's take a look at this. So first, I have the equation of motion. So this is a single degree of freedom system. Theta is the pitch. On the left-hand side of this equation, the first equation is the structural part, which we already know. So we're assuming we already know the structural properties. So damping, stiffness, and so forth. What we want to capture is the aerodynamics, which is the coefficient of movement on the right, shown in red. And that's a function of pitch displacement, pitch velocity, and pitch acceleration. So if we take the thin airfoil theory and add a bunch of nonlinear terms to it, so you'll see that E3 theta cube and E4 theta squared theta dot, those are terms I just put it in there. And the rest of the components are from the thin airfoil theory. So quasi-steady. So first two models are quasi-steady thin airfoil theory, and the last two models are from the unsteady thin airfoil theory. So I came up with these 4 models, and you'll see on the end of these 4 models, I have a sigma xi term. That's the model discrepancy error term. So I'm assuming Gaussian white noise for the model error, and sigma is going to capture the strength, the standard deviation of that. And I'm treating sigma as an unknown parameter along with E1, E2, E3, and E4, for example, in M1Q. So since I didn't know about nonlinear aerodynamics, I had 4 different models that I think could represent the aerodynamics. And each of these models has tuning knobs, or parameters that I need to compute. And it also has the model discrepancy error term, which I'm also treating as unknown. And then I have the measurement equation. So my observations are noisy. So if I go back, you'll see it's not very clear here, but if you see the time history, there's just random noise added onto it. So this is the noise that's created by the sensor that captures this displacement. So we have to capture that. So in the measurement equation in the bottom, you see that observational noise component. So we have already captured the data uncertainties and the observation noise that we had. And we also have the model discrepancy error added onto each model. And we also have the model selection error by proposing these 4 different models that could fit or that could represent the aerodynamics of this self-sustained oscillations. So we have captured 3 types. Sorry. Did anybody have any questions?
Yeah, is it a time series of errors?
Say that again, please. Time series of.
So you're adding some noise to your data, and I want to know: are you adding a time series of noise, or are you adding just one noise per experiment?
No, this is time. So these parameters are time invariant. They're not varying with time. The only thing that varies with time is theta, and obviously your white noise, right? It's going to have different realizations.
Yeah,
Well,
can I ask something?
Yep.
This is Torben. I mean, if you're saying you're adding, I mean, it's just a model. You're not adding anything. You're just modeling.
Right.
Yeah. Okay. Just to avoid any misunderstanding.
Yeah.
Thanks, Torben.
Yeah.
But I guess it's like a decision, right, to make these uncorrelated in time. I mean, could you have made your noise correlated in time? Would that have affected your results?
Absolutely. So there is we did work on that. Yeah, we added colored noise to it. So that's we have a publication on that, and I'll point you to that publication. But in this, the work I'm presenting today, we just assume it's Gaussian. Gaussian noise is typically, I mean, if you're just starting with very simple inverse EQ, we just assume Gaussian noise. But yeah, as you try to perfect and fine tune your model, you try colored noise, try more over parameterized models, and you try to find your way to the best model out there. But yeah, and here I'm just assuming Gaussian noise, but we did work on color noise component to this.
Because I guess the sensors you use, like, they probably don't give you any guidance about what to do for coloring your noise.
Well, the sensor noise is in the observational noise. That's the epsilon. The sigma is the model discrepancy error. Those two are different.
So epsilon is not a time series?
It is time series. Yeah, that's the K subscript. So it is.
And epsilon represents your model, or your measurement device error.
Gaussian, yeah.
So it would be so nice if the manufacturer, that measurement device, told you the correlation of your error in time, right?
That's right, but that's not going to be exactly, you cannot backtrack to sigma because there's a complex relationship. You're capturing theta, and from theta, you're trying to determine how the frequency content of your model discrepancy error is. So there's not exactly a linear relationship. If your epsilon, if your sensor tells you it's a Gaussian noise, that doesn't necessarily means your model discrepancy error is Gaussian. Because you're capturing.
Definitely, yeah, I definitely was not trying to make that claim. Just in this project, we've run into this question a ton about temporal correlation of measurement uncertainties. Just wanted to get your full thoughts on the matter, but thanks very much for fielding the question.
Yep, absolutely. Yeah, this is so observation noise. I should mention that we already know. I'm not including it as part of the parameters that I need to tune. So what we did was we ran wind tunnel experiments with just wing stationary, and we captured the response and took the mean and standard deviation of that, and that was our epsilon K. We didn't have anything from the manufacturer, so we're assuming that we know the observational noise by capturing the wind tunnel, the pitch displacement at static, angle of attack 0 degrees. And the only thing that we're trying to capture is the model discrepancy error, which is parameterized by sigma. Okay, so Bayesian inference is a natural way of trying to do this inversion while trying to quantify the uncertainty. So there's three things that goes into Bayesian inverse modeling. There's prior knowledge. So for example, here in my model M1Q, my E1 and E2, I have some understanding of that from my understanding of the thin airfoil theory. So I may want to include that information in there. So these parameters are not just data-driven components. There's some background information to it, which I would like to include. For example, parameter B in my uncertainty models is a Wagner coefficient, which I know its values, so I want to include that information while also trying to estimate it from the data. And Bayesian inference modeling allows you to include that. There is laws of physics, so obviously my model structure is motivated by the thin airfoil uncertainty theory. And then there's field observations, my pitch displacement captured from the wind tunnel. So all three things goes into this Bayesian inverse modeling. So my first step is I have candidate stochastic models. So stochastic means I have that model discrepancy errors, and I'm also capturing the observational noise. That's why I'm calling these stochastic models. I have prior parameter PDF. So PDF means probability density function. So I have those for my parameters. The next step is to compare the models. So there's Bayesian model comparison, which uses something called log evidence, which is basically, if you look at the first equation from Bayes' theorem, so you have P of phi given D. Phi is your parameters that you need to estimate. So E1, E2, E3, E4, including sigma. And D is your the time history that you captured from internal. So you're trying to compute the posterior parameter PDF. And you can write this equation. So you have P of phi, which is the prior distribution, and P of D given phi is the likelihood function that captures the model. And then denominator is usually ignored because it's an integral for parameter estimation purposes. And you write this equation proportionality sign. And then you use Markov chain Monte Carlo methods to estimate your posterior parameter PDF. Obviously, if you just want to do parameter estimation, you don't have to worry about P of D, which is the denominator in the first equation. But if you want to compare a bunch of models, this P of D becomes very important. And it's actually called evidence or model evidence. And this is basically a parameter, a number that quantifies how likely the observation came from a particular model. So you can use this model evidence to compare different models that you have to capture the physics. So, and it's basically what it's doing under the hood is it's trying to find a balance between data fit and model complexity. So you don't want your model to be too over parameterized. And also, because it will then fit the data very perfectly, even so it will try to capture the noise in the data, and so your extrapolation capability may be degraded because if the model is overfitted, it's not going to do a good job of predicting outside the regime of your training data. And also, you don't want your model to be too simple, right? So model evidence basically try to find a balance between the two. So there's two steps, and then fifth step is Bayesian model averaging. So let's say you end up with 2 or 3 models that you think are good, and there's some probability associated to them. You can use actually a bunch of models to make predictions instead of just using one. Obviously, you can select the model with the highest model evidence and just go with it. In that case, you don't need to do much Bayesian model averaging. But if you end up with 2 different models that you think are appropriate, you can use both of them to make predictions. And once you have your model, you can do this design optimization and sensitivity studies or anything you want to do with it. So these are the results. So on the left, the table shows you the probability, and the fourth column is a probability of individual model given the data and the model set. So this is basically a normalized version of model evidence. And what it's telling me is there's 80% chance that the second M2U basically created this data. So that's what I'm going to do here. I'm going to select this model out of these bunch of models that I proposed, and I'm going to estimate the parameters. So on the right, you see the probability distributions that came out from the Markov chain Monte Carlo simulations of the posterior PDF. So I have the distributions of the optimal model. And now, given these distributions, I can then go and use it to make predictions. So on the left is what I have after I've done the Bayesian inverse modeling of this. So I have the equation of motion. Obviously, I knew everything about the structure. Only thing I need to worry about was their aerodynamics, which I've now able to capture using this Bayesian inverse modeling. This is my model structure. This is my parameter posterior PDF. So you'll see the sigma there on the bottom. The text is very small, but there is a probability distribution of sigma there. So we are estimating sigma, which is basically the standard deviation of your Gaussian model discrepancy error. And then you can use this entire apparatus to make predictions. For example, I'm trying to predict Wagner function here and comparing it to prior estimates of this function. Obviously, the pink region is basically your the confidence interval of your prediction. So the key idea is here, anything you want to predict, you'll get probabilistic information about it. And this probabilistic information is basically capturing your observational noise, your model discrepancy error, your model selection uncertainty, all the uncertainties that you have captured in this process. So with that, I'll just mention that there are, in my PhD, I try to basically perfect this whole process, starting from parameter estimation to model selection. Then I moved to sparse learning. And I think in the later part of my PhD, I tried to capture the, I tried to deal with the issue of overfitting. So usually when you have these low to mid fidelity models, you tend to over parameterize them. And over parameterization leads to overfitting if you don't have too much of data. And overfitting can cause problem when you're trying to extrapolate. So there is a need to deal with overfitting. So I went to machine learning literature and found this sparse Bayesian learning algorithm and tried to implement it for physics-based models. So, and as I mentioned, and I still maintain contact with my old research group, so you'll see publications that came very recently. Obviously, some of the publications are after I left, after I came to NREL, and my publications for my PhD were published later. So I encourage everyone to, if you need more information, you can read these papers. But it's basically trying to do Bayesian inverse modeling and trying to perfect this for situations where you don't have much data and you don't want to do high fidelity simulations. So talking about wake modeling, I don't know how I'm doing on time. Eric, please interrupt me if I'm going over time, but this is my last slide. So in wake modeling, is now we're trying to have computationally efficient predictive models of wake. So I guess in that respect, it shares some of the motivation that with the work that I did. And similarly, it's CFD. I mean, you can run CFD, but it's very expensive. Time consuming, computationally expensive. So empirically driven big models are popular because they're you can run them quickly and you're able to capture the underlying physics in a reasonable way. And they're usually trained using high fidelity simulations or field observations. The problem is that we're not able to capture the entirety of the wind conditions or layouts. So there's some, in that respect, there's some I guess we could say there's like limited data or limited training data available to train these wake models. So, and obviously there could be multiple models that may exist. So for example, the superposition of wakes, there's a bunch of approaches that you could use. So there's some uncertainty in that respect. So I guess I tried to compare what wake modeling with what I did, and I saw a lot of similarities. So inverse UQ is definitely it needs to happen for wake modeling. So this is definitely a lot of uncertainties going on there. So how could Bayesian inverse modeling help in this situation? So I mean, it could include modeling and data uncertainties, like I mentioned, by adding, let's say, a model discrepancy error term, by proposing a bunch of models and then comparing them using Bayesian model comparison. You could propose multiple, heuristic or empirical wake models and then compare them. You can deal with overfitting. So I was reading a few papers and they mentioned there's, you don't want to over parameterize wake models. Well, there is a way, as I mentioned, using this Bayesian model comparison or sparse learning, you could propose an over parameterized model and the algorithm will tell you, okay, these parameters are redundant. You probably need to remove them if you want to enhance the extrapolation capability of that model. So there is some approaches there that could deal with over-parameterized models. And again, once you have the trained optimal model and its parameters estimated in terms of probability distributions, you can use keep using that model in the Bayesian framework to inform future data collection efforts and so forth. So, I mean, there's a lot of things that within Bayesian inverse modeling that could be done that could help advance the wake modeling effort. So, I'll just stop there, and Eric, I'll turn back to you. Thank you.
Great, thanks very much, Rimple. It was a really interesting presentation, and appreciate your time today to share your work with us. Yeah, I thought that was really interesting, especially kind of learning about the log evidence function and how you can use that to evaluate the model itself. Wasn't familiar with that before. Any questions for Rimple? No? All right. Here's a question from Brian.
Hey, thanks for the presentation. That was super informative. I've been trying to do some similar stuff with Flores and looking into some parameter optimization. And the parameter set for Flores is pretty large. And a lot of the parameters have extremely similar effects. So we've got sensor biases in the wind direction. You've got one of those per turbine in large farms that becomes very challenging to deal with computationally when you're doing Markov chain Monte Carlo methods.
Yeah.
Or sequential Monte Carlo methods. So I've been trying to do variational approaches instead, but I'm having a hard time dealing with those coupled parameters that have very similar effects. And we only have power measurements and the cell position measurements. So do you know any good strategies to find the most likely parameter values given strong coupling between those engineering parameters in terms of like, yeah, I'll let you answer. Hopefully that was clear.
Yeah, I had similar issues. So in the model that I shown here, I actually took the thin air field theory, and it only had E1 and E2, and I added like 10 nonlinear terms to it. It's like theta to the power 7 and theta to the power 9. I just throw the most complex model out there. Obviously, that way, if you just have cubic nonlinearity, your theta cube, theta to the power 5, theta to the power 7, those parameters are all going to be related to each other. There's going to be very strong correlation. So what I realized was we probably need to run some model selection or sparse learning approach before we can actually go about estimating the parameters. So there's several out there. You don't have to do Bayesian. You can just do maybe there's approaches that would just add a regularization term to your maximum likelihood estimate. So you could try that. That will tell you, okay, out of these 100, only 50 parameters are important. Then you take that model and do Bayesian inverse modeling. And that way you don't have to go into variational approach because you're dealing with less number of parameters, and you can run your MCMC with that as well. Obviously, you can keep doing variational stuff, but I think first there needs to be a sparsification of your model. And so there was a paper that I wrote about nonlinear sparse Bayesian learning. So I was doing sparse learning, basically trying to prune the parameters space of my model so that I'm dealing with an optimal model. But I was doing everything in Bayesian framework, but it doesn't necessarily have to be in Bayesian framework. So as I mentioned, regularization. There is information criterias that are out there, like Bayesian information criteria. There's Akaike's information criteria that's very popular. infrequentist modeling. So anything, because that doesn't require you to capture the whole posterior. You just need to optimize your maximum likelihood, your likelihood function. And using that, you can just compute those numbers, and that will let you compare the two. So yeah, yeah, this is a problem that sparsification is something that needs to happen before estimation. Yeah.
Thanks. I'll definitely take a look at those and see what I can take from it. Do you mind if I ask a quick follow-up question?
Sure.
So I've been thinking about this a little bit lately, that the kind of Gaussian assumptions seem standard in statistical modeling. Like you assume that your model structure is capable of representing the data generation process in an unbiased way. So you have a zero mean.
Yeah.
Gaussian errors, like we were talking about earlier.
Right.
And that those errors should be uncorrelated in time, hopefully, if your model specification is good. But we are seeing that a lot of our sensor biases change over time. And so our observational noise ends up being correlated in time quite a bit. Did you have a reference at the end to your work on the colored noises?
Yes. So combined selection of dynamic model and modeling error. So in this paper that one of the grad students wrote that I was part of, we were trying to estimate the model and the error representation, both of them at the same time. So in this one, I assumed I'm a Gaussian white noise error. But in this paper, we relaxed the assumption and assumed a colored noise. Obviously, if you have color noise, you can end up with more than one parameters. It's just not sigma. There's going to be another parameter. So you relax that assumption. Obviously, that will lead to more parameters, but that's fine. I mean, if you have a very simple model, your model noise error, model discrepancy error will never be Gaussian, uncorrelated. Never be white noise. The more complex model you have, your errors are going to increasingly look like white noise. So while you're trying to optimize this model, you also have to make sure that you're relaxing that assumption. So in this paper, we tried to explore that.
So if you were to fit your model parameters, assuming Gaussian white noise when the model errors are colored, does that bias your parameter estimates?
Yes, it does. Yeah.
Okay.
So if you assume Gaussian white noise, it's going to affect your parameters. Yeah, because you're estimating sigma at the same time as other parameters. So it's always, yeah, absolutely.
We're kind of running into something similar where if we assume uncorrelated noise in our sensors in the field, it really influences the results than if there were colored errors in the sensors in the field.
Absolutely.
Seems like a big open problem.
Yes, it's really a problem. Yes, I cannot stress that enough. Yeah, I was lucky that I was allowed to get away with Gaussian noise, but the students that came after me, they're now dealing with this problem. But yeah, this is I mean, we read papers and everybody assume Gaussian, but there is a caveat with that. You're gonna affect your parameters in some way. So.
And I talked to the measurement people. Like, there's quite a few people here that are just devoted to measurements, and they don't think about this stuff. They say, yeah, of course it's uncorrelated. But it just surprises me that we don't have some sort of calibration or temporal time scale, or I don't know what. Somebody describe this.
Yeah. So yeah, I mean, so I think it's all come down to simplifying your life. So people just went with Gaussian just to make things simple. And so now, as you mentioned, it's not always possible that it's not always Gaussian. So we relax that assumption, assume color noise, have parallel models for error. So you have two streams. You have your bunch of models for your representation of physics, and you also have corresponding bunch of models for your error term. And then you try to, if you have 10 models for, your physics and 10 models for your error, you're going to end up with, a lot of models by permutation combination. And so you throw this at Bayesian model comparison, and that tells you, okay, this combination of dynamics, or this combination of dynamics plus your model error is the best out there. The problem with sorry.
Please. I was going to say that's all well and good for calibration, but I think most of us are more thinking about validation, where we can't use the model that matches the data the best because we want to validate the model in the first place.
Right. That's true. Yep. Validation is definitely a beast.
Yeah, for control, that ends up being a little harder. Like you can have a model that predicts the data well, but it predicts it for the wrong reasons because there's so much coupling between the parameters. So when you try to do control, it ends up being, you're implementing the wrong control strategy because your model looks like it's validated well, but it's not actually doing what you want it to do. And that's something we've been struggling with a little bit.
I should mention that in the model complexity term of this Bayesian model comparison, you see the log of P of phi given D in there. That means it includes the entire information, the joint distribution of parameters when it captures model complexity. So if you go to Akaike's information criteria and all of these, they measure model complexity in terms of number of parameters a model has. That may work for, let's say, a regression, polynomial regression and stuff like that, but it may not work for complicated models that have nonlinearities. So this quantification of model complexity captures the entire probability distribution. So if you have a strong correlation between two parameters, it's going to increase the model complexity. So, and if you increase the model complexity, the model evidence will favor the model that has one of those parameters removed. So it's sort of under the hood tries to, alleviate strong correlations by removing a bunch of parameters. But again, as you mentioned, there's just a lot of other things going on at the same time as well.